Hi everyone, this is a brief presentation about the Open Dependability Exchange Meta-Model. My name is Victor Luiz Grec and I'm a PhD student at the University of São Paulo in Brazil. First, I would like to summarize some points. The first point is the context. So, safety-critical componentized systems and system of systems have the need for exchanging dependability information at runtime. So we want to assure the dependability level of components that we are connecting after the design time. At runtime, all the systems are already developed, and we need to assure their safety level. This dependability information must be provided in a multi-tier supply chain. That is, we have to choose which dependable information we want to provide to our vendors, customers, and so on. And it must be two independent. The second point is how. How does ODE accomplish this? ODE was created based on engineering stories from the industry. And when we instantiate a ODE meta-model, we have a so-called DDI, which is the acronym for Digital Dependability Identity. The last point is the what. So ODE captures the essence and relation between safety and security related artifacts created during the entire development life cycle. The DDI, which is the instantiation of the ODE meta-model, is an artifact which provides modularized and formalized dependability information for cyber-physical systems and its components. Here we are going to do an overview over the ODE packages and explain the relation between a few elements here. This is the whole picture of the ODE package. We can highlight here the more important packages that are the design, dependability package, failure logic, and base package. You can see that dependability and failure logic, they have sub-packages, and we are going to pass through all of them. Here in the base package, we have the base element, which is abstract with ID, name, and description. Almost all elements on the ODE meta-model extends from base elements. We also have key value map, values, and an enumeration for time units. Here in the design package, we can highlight the most important elements that are systems, functions, ports, and signals. Where we are, when we are talking about system, we can represent the system as a logical component or a physical component. We also have here uh, the representation that all elements extends from base elements and how does the design package exports its own elements. So we have the exportation of system and function, and also how system, function, and port are associated with other elements inside other packages. So we have relations with failure model, asset, dependability requirement, assurance level. Also in the core of this diagram, we have maintenance procedure, malfunction, failure, and standard. Entering the failure logic package, here the most important elements for this presentation are failure and security violation. Security violation is a specialization from failure. With security violation, we can relate safety-related artifacts with security-related artifacts. So security violation relates to attacks, uh, and this enables us to do a co-analysis using safety and security. We also have here specializations from failure model, which leads us to the sub-packages, each sub-package for one technique. we have the FTA, FMEA, and Markov packages. The FTA package, which represents a fault tree analysis, we have connections with failure and failure model. We have here the elements cause type. The gate can be an AND gate, OR gate, SHOR gate, and cause type can be an input event, output event, basic event. The FMEA, we have the entries related to failure, and FMDEA entry related to probDis, which is the probabilistic distribution inside the failure logic package. Here in the Markov package, we have the Markov chain technique with the elements transition and state, also related to failure and probDis. Here, the dependability package, we can highlight some core elements, which are the maintenance procedure, measure, and measure type. We can also highlight sub-packages inside the dependability package, which are the domain package, data package, requirement package, and HARA package. Here in the requirements package, we have the most important elements as dependability requirement, which has the specializations of safety requirement related to hazard inside the HARA package, and security requirements we have that has the association with security capability inside the Tara package. We also have far more associations for dependability requirements, which are assurance level, measure, maintenance procedure, and failure. The domain subpackage is very simple. We have standards with the specialization of safety standards and some assurance levels to accomplish. Uh, the HARA package, which is an acronym for Hazard Analysis and Risk Assessment. We have the most important element here is hazard, which has associations with measure and failure. We also have the risk assessment associated with risk parameters. Risk parameter has three specializations, which are situation, accident, and operation measure. They have the properties likelihood, severity, and controllability, respectively. And this allows us to achieve the ASIL described in the ISO 26262, which is the Automotive Safety Integrity Level. Here are the associations with hazard that I already described, and how the HARA package exports its own elements. Lastly, we have the TARA package. Uh, TARA stands for the Threat Analysis and Risk Assessment. Here, the most important elements for us are the attack association with security violations inside the failure logic package. These give us the connection between security events and safety events. We also have how the all the elements that extends the base element representation, and that's it.